Hello, my name is Quinn, and my project is on total synthesis of Meayamycin B. So what makes Meayamycin B interesting? Well, Meayamycin B is a modulator, and it acts as an inhibitor for SF3B1 splicing factor. SF3B1 contributes to the development of leukemia and cancer cells. It's also known as the cancer gene because it is frequently mutated in many cancers, which controls how specific segments of RNA are joined together, also known as RNA splicing, um, to make a full messenger RNA, which is used to make proteins. So the defect of SF3B1 gene is unknown, and what makes Meayamycin B significant is it's able to bind to the receptor and change the response to the stimulus. There's been research showing that it promotes pro-apoptosis, also known as programmed cell death, and really good for halting pre-RNA splicing in live cells. So it's very useful in biomedical research regarding stopping tumors and cancer cells from proliferating. So our objective is to synthesize myosin B. Uh, what they started with was a left-hand fragment and a right-hand fragment. So here is the left-hand fragment, and here is the right-hand fragment along with the coupling fragments. Today I'm going to be focusing on the Vedic approach, the first 5 steps, along with 2 additional steps leading to the right-hand fragment, and then our new reaction, which is olefin metathesis, to couple the 2 fragments. So researchers began with the preparation of the right fragment with ketone 18. This first step was alpha halogenation, with reagents bromine and methanol beginning at 0 degrees Celsius. This yielded a 90% yield. So I set up a mechanism, and we're going to start with the carbonyl group attacking a proton from the methanol. So now we have a methoxide, and the methoxide is a good nucleophile and a good base. Also notice that we do have 2 alpha positions, and these protons are very acidic. So the methoxide is going to attack one of the protons. Notice that I'm going to attack the less substituted position because that's what we want. And it will form a resonance stabilized enol. So that double bond is going to act as a nucleophile and attack a bromine. And the other bromine is going to attack the proton where that oxygen is. And that's how we get our product with HBr. So right after alpha halogenation, the next step is preparing the Wittig reagent using reagents triphenylphosphine and toluene, followed by the treatment with aqueous NaOH. So Wittig elide formation is going to begin via SN2 with triphenylphosphine attacking and bromine leaving. And so the CH bond adjacent to phosphorus is relatively acidic, so the strong base NaOH is going to depronate a hydrogen bond, therefore forming our elide. So we have 2 hydrogens here, and OH is going to attack one of those hydrogens, and therefore forming that pi bond for our product. So what happens next is the Wittig reaction proceeds with the stabilized Wittig reagent, replacing the carbonyl group from the acrylein with a carbon-carbon double bond. and we get a low yield of 24% for ketone 21. What makes this significant is even though that the reaction wasn't efficient enough, the product could still be formed using inexpensive reagents and easily purified through extraction. So why was the product yield at 24%? Well, molecule 25 can rearrange itself and create a more stable molecule known as molecule 25A. Phosphorus has an affinity for oxygen, so it will bind with oxygen, and that is the driving force. The right molecule is more stable, therefore equilibrium will shift towards the right towards 25A. And this yield will be the remaining 76%. So it begins with the electrons kicking down, forming our alkoxide, and then it will undergo proton transfer. So now that you have a anion and a cation on the phosphorus, it's going to bind together and therefore create our 25A product. So next, molecule 21 was cooled to 0 degrees Celsius and underwent reduction of the ketone group with sodium borohydride and methanol. So borohydride is going to attack the ketone. This is going to kick up. That's going to form an alkoxide. And the alkoxide is going to take a proton from the methanol, therefore making molecule 22. After that, molecule 22 underwent epoxidation performed under -20 degrees Celsius, yielding molecule 23. So if you remember from chapter 13, the epoxidation is a sharpless asymmetric epoxidation. The reaction is highly enantioselective and very successful in allylic alcohols. As you can see in molecule 22, we do have an allylic alcohol. The catalysts are comprised of titanium tetraisopropoxide and one enantiomer of diethyl tartarate, also known as DET. DIPT or diisopropyl tartarate can be used as well. The reason why we use this catalyst over DET is DIPT's ability to sometimes achieve higher selectivity. So positive diisopropyl tartarate will form an epoxide above the plane of molecule 22 and therefore forming molecule 23. This is done under titanium tetraisopropoxide, which forms a chiral complex with either positive DIPT or negative DIPT, and this complex serves as a chiral catalyst. So in the presence of this catalyst, tert-butyl hydroperoxide can convert the alkene into an epoxide. The stereochemical outcome of this reaction depends on whether it was formed with the positive enantiomer or the negative enantiomer, and that's how we get molecule 23. Molecule 23 then underwent oxidation by treatment of DCM and then tetra-N-propylammonium peruthenate, or TPAP, and co-oxidant N-methylmorpholine and oxide, NMO. Remember that in the book, NMO was a co-oxidant used to regenerate osmium tetroxide, a reagent used for syn dihydroxylation. Because we have a secondary alcohol in molecule 23, the alcohol group will yield a ketone in the product. So basically, this is a Ley-Griffith oxidation reaction. The catalysts include TPAP and NMO, and the mechanism is very similar to Des-Martin, except that the NMO regenerates the TPAP. Not only that, the area of focus is primary and secondary alcohol groups, and it will have excellent yields. The only drawback is TPAP is very expensive. As you can see in the mechanism, we do have a primary alcohol right here, and the ruthenium ion is going to attach in that position and therefore form a aldehyde in this example. And that's how we get molecule 27. So after oxidation, ketone 27 was treated with camphor sulfonic acid, also known as CSA, along with dichloromethane. The mixture was stirred at the same temperature for 19 hours, and ketone 27 underwent anti-Baldwin-Nicolau type cyclization under acidic conditions. So the OH group bonds to one of epoxide's carbons, causing a ring opening, followed up by a workup, and that's how we get ketone 28. Our yield is 70%. After that, THF and dibromomethane was added and then cooled to negative 78 degrees Celsius. Then N-butyllithium was added. So bidentate ligands or chelating ligands are Lewis bases that donate two pairs of electrons to a metal atom. In this case, the two oxygen atoms have lone pairs that bind to the lithium in two places, allowing for the molecule to be subjected to nucleophilic attack through bidentate chelation model shown above. This added another carbon atom from what I assumed to be from the dibromomethane that was added to for the right fragment of Meayamycin B at 73% as a single diastereomer. The final step to synthesize Meayamycin B is cross-olefin metathesis, also known as cross-alkene metathesis. This is a reaction we just learned in chapter 23. The objective is to couple the two olefin substrates together using a nitrocatalyst. Characteristics include good reactivity, but very poor functional group tolerance and EZ selectivity. So why do we use nitrogrella as our catalyst? Well, it's a generation 2 Grubbs catalyst, so it's more stable and more active than original versions. Notice the nitro group on the catalyst that leads to it to be more dramatically active. Because it's a Grubbs catalyst, it can tolerate variety of functional groups and has high stability in air and various solvents compared to Schrock catalysts. It's an effective catalyst for ring closing, cross, and E9 metathesis. In cross metathesis, this catalyst can perform reactions at lower temperatures while favoring high selectivity in conditions that make E and Z selectivity difficult. The mechanism begins with initiation. The nitrogrella catalyst reacts with either fragment. I'm going to start with the lead fragment, and this gives a metal alkyl-iodine complex, which is formed via 2+2 cycloaddition. And then fragmentation occurs, therefore yielding our byproduct and intermediate. The byproduct is only produced in small amounts because the metal complex is only present in a catalytic amount. Take note that this is the same process if you were going to begin with a right fragment first. So after initiation, the intermediate's going to interact with an alkene of the left fragment, and that undergoes 2+2 cycloaddition and fragmentation once again. So this is going to yield our product and regenerating a catalyst to be used in the process all over again. So the regenerated catalyst interacts with one of the fragments and undergoes 2+2 cycloaddition followed by fragmentation once again to yield the intermediate that reacts with another alkene and ethylene gas that bubbles out of this mixture. So the ethylene gas drives the reaction towards the formation of the alkenes, therefore yielding excellent yields. So here is the mechanism summed up in a catalytic cycle. During the process, homocoupling and heterocoupling of olefin fragments can occur. This yields three different products. Assuming full conversion, if two olefins of similar reactivity react in a cross-metathesis condition, a maximum of 50% yield of the desired product would be obtained, while 25 of each of the two homocoupling products will be formed. In this case, only 20% of the desired product was produced, meaning that the selectivity favored the homocoupling products. The percentages of homocoupling products were not specified. So in conclusion, the overall yield of Meayamycin B was 0.82%, but the significance of this experiment was better access to left-hand and right-hand fragments using commercial available and less hazardous reagents. Not only that, it was very price effective, specifically to the right-hand fragment. Previous methods cost $753 for 1 millimole, and this method only cost $204 per millimole. So we were able to synthesize this molecule in 11 steps in the longest linear sequence with a total of 24 total steps. So here are my references and thank you for watching.